Welcome to today's on-demand webinar about the use of Polyclar Brewbrite stabilizer in beer. In this presentation, we will discuss beer stability and the process of haze formation and haze prevention. We will introduce Polyclar Brewbrite stabilizer, provide some comments on pilot and commercial trials, and then summarize our findings. What do we mean by drivers for beer stabilization? We want to answer the question of why should a brewery spend money to stabilize their beer? Consumers expect better quality and product consistency. The new breweries are larger with expanded distribution areas. Beer has to travel further from the brewery, and this requires beer to be stored for longer periods. There is a challenge in producing quality products in developing markets that can compete with imported beers. Domestic producers don't want imports to take over. There is also a need to reduce costs, both production costs and returned beer costs. Beer is sometimes returned to the brewery if something is perceived to be wrong with it. There is also potential loss of market share from someone not having a good experience with their product. A suitable definition of beer stability is the ability of beer to resist the formation of non-biological colloidal haze. The end of useful shelf life in beer is generally considered to occur when a beer develops haze of 2 EBC. At 2 EBC units, you are visually able to perceive haze. To demonstrate the impact of environmental stress on beer, we took packaged beer and subjected it to different environmental conditions. One lot was stored cold, one lot was stored at 40 degrees Celsius, one lot was cycled between 40 and 0 degrees Celsius, 24 hours at a time, and one lot was kept at 40 degrees Celsius and also shaken at the same time. Shaking beer at high temperature produced more haze than any other storage condition. This has a lot of practical implications, particularly in countries where the summer temperatures are very warm and the beer has to travel in trucks on very bad roads. These beers will be prone to produce much more haze. The precursors for formation of haze is complexation between haze-giving polyphenols and haze-sensitive proteins. The structure of haze-sensitive protein is shown here. These proteins have high molecular weights, they are proline-rich, and originate from the Hordine fraction of malt. They transfer through the wort and finally to the beer, where they complex with the polyphenols to form haze. On the left of this slide are the monomeric polyphenol haze precursors, such as catechin and gallocatechin. These monomeric polyphenols condense to form dimers and trimers. An example of a dimer in this slide is prodelphinidin. On further oxidation, these dimers and trimers polymerize and form very large molecules called tannoids. The larger the polyphenols are in terms of molecular weight, the more polyphenolic OH groups they will have, and these OH groups then readily combine with haze-giving proteins to make protein polyphenol complexes, which will result in the formation of haze in beer. Many years ago, Chopin proposed that haze in beer is formed by protein polyphenol interaction. Carl Siebert further developed this model and noted that not all polyphenols are the same. There are haze-forming polyphenols as well as polyphenols that do not contribute to haze. Similarly, on the protein side, Siebert distinguished between haze-giving proline-rich proteins and low molecular weight foam-producing proteins. It is the proline-rich proteins that combine with the polyphenols to form haze. These polyphenols have to have at least 2 ends to combine with proteins in order to form haze. Polyphenols could have 3, 4, or 5 ends. If they don't have at least 2 ends, the chain cannot grow. We see this in haze formation where the chill haze increases with time. The longer you keep the beer warm or agitate or give any impetus to haze formation, the chill haze and total haze will increase. That's basically because these chains of proteins and polyphenols grow over time. This slide shows the O'Rourke model for haze formation. Even in very clear beer, when it is first filtered, the monomeric polyphenols combine with protein but do not contribute to haze formation. Even if the beer is absolutely clear, complexation has already begun. The reason you are not seeing haze is that the polyphenols are monomeric with small molecular weights. On oxidation, the monomeric polyphenols convert to dimers and trimers, and these combine with proteins to give you the reversible chill haze. This is the haze that appears in a bottle of beer when it's chilled and disappears when the bottle is warm, say by putting a beer on your kitchen table. On further oxidation, these dimers and trimers convert very reactive oxidized tannoids. As we saw in the previous slide, these tannoids have a number of anchoring polyphenolic OH points that make them very reactive, so they combine with protein to give you permanent haze. One thing to notice here is that the formation of permanent haze, the tannoids cross-link a number of proteins, so you get these very large tannoid protein formations. We always say that tannoids are the number one enemy of beer. For beer to be stabilized, you have to remove all the tannoids. By the same token, you have to remove about 40% of the monomeric polyphenols, which in time will give you the secondary tannoids. This slide presents some evidence for the models I've just described. For this, we did a very simple experiment. We took beer and overstabilized it with PVPP using a dose rate of 100 grams per hectoliter. At this high dose level, most of the polyphenols were absorbed out of the beer and only the haze-giving proteins were left. Then we added 3 different types of polyphenols to this beer separately: catechin, tannic acid, and oxidized catechin. Catechin is a monomeric polyphenol, tannic acid is a tannoid, and oxidized catechin represents dimeric and trimeric polyphenols. You can see on the x-axis that these were added at different dose rates. This addition produced a dose-related response for both tannic acid and oxidized catechin. We found that catechin did not give an appreciable rise in haze formation, indicating that the polyphenols have to be oxidized before they will participate in haze formation. Here you can clearly see that the red and green lines have fairly low values at 10 grams per hectoliter compared with 50 grams per hectoliter. The dose-related response is clear for both tannic acid and oxidized catechin. This is a model of haze formation showing total haze on the y-axis and storage time in weeks at an elevated temperature of 37 degrees Celsius on the x-axis. Before we did this work, we expected this graph to show only the incline phase, indicating that haze formation is directly related to storage time. However, what we found was that this graph was biphasic. There was a clear lag phase followed by a clear incline phase. During the lag phase, a large pool of tannoids is being generated. When you get a large enough amount of these very reactive tannoids in your beer, they readily combine with the haze-giving proteins to give you the incline phase. The slope of the incline phase gives you the rate of haze formation. This is the basic structure of the building block of PVPP. The important thing to note is the relation of the carbonyl group to the nitrogen. Because of their proximity, the carbonyl group has a very strong partial negative charge. This partial negative charge on the carbonyl group readily combines with beer polyphenols, which have a partial positive charge on the phenolic OH groups. The hydrogen bond between the carbonyl and the polyphenolic OH group is very strong. You can see some similarity between this structure and that of the amino acid proline. The preferential mechanism is hydrogen bonding, but there is also some evidence of pi bonding and polar interactions which further strengthen the interaction. Now we'll take a look at Polyclar Brewbrite Stabilizer product and application information. Polyclar Brewbrite Stabilizer and Wort Clarifier is a composite of a selected carrageenan and micronized PVPP. It is added to the brewing kettle 10 minutes before the end of the boil. The boiling mixes the Polyclar Brewbrite Stabilizer and Wort Clarifier together with the wort. On the left side of this slide is the structure of kappa-carrageenan. Irish moss, the source of carrageenan, is a mixture of lambda, iota, and kappa-carragenans. Ashland selectively uses kappa-carrageenan to make the admixture that is Polyclar Brewbrite Stabilizer and Wort Clarifier. Kappa-carrageenan is made up of alternating galactose units. This is a galactose unit with an ester sulfate group followed by an anhydrous galactose unit. The presence of a large number of ester sulfate groups in kappa-carrageenan gives it its strong negative charge, which enhances its functionality. The strong negative charge interacts readily with the basic proteins, making protein with a positive charge. Kappa-carrageenan is thermoreversible. It is free-flowing when it is hot, but gels as it cools. When the wort is transferred to the whirlpool, the cooling temperatures cause the kappa-carrageenan to gel, forming flocks with the reacted proteins that settle out when they get large enough, leaving a very clear wort. Additionally, the inclusion of PVPP in this composite gives you upstream removal of tannoids in the brewing process. Tannoids are the number one enemy of beer, and the upstream removal of tannoids helps to clarify and stabilize the wort. Wort clarity and beer colloidal stability are key factors in shelf life. PVPP is the method of choice for colloidal stabilization of beer. Kappa-carrageenan, also called kettle finings, is very effective at reducing non-microbiological particles, or NMPs, in the wort. NMPs act as templates to which the protein polyphenol complex attach, accelerating haze formation in beer. Both materials are widely used in brewing. The stabilization and clarification of beer can be simplified with the addition of Polyclar Brewbrite stabilizer and wort clarifier to the wort. No specialized equipment is needed, no slurry tanks or dosing pumps. It has good hydration and mixing in the kettle and is removed with the trube. Polyclar Brewbrite stabilizer and wort clarifier is used in essentially the same way as kettle finings. It is added as a powder to the wort kettle 10 minutes before the end of the boil. It can be slurried in hot water and added to the kettle, or added with the last hops in automated systems. Adding Polyclar Brewbrite stabilizer and wort clarifier to the boiling wort reduces haze in the finished beer and causes increased settling out of trube. This slide shows the improvement in wort clarity before and after Polyclar Brewbrite treatment. Now we'll review several pilot scale studies. This slide lists the protocols for making the 100% malt lager. It was fermented for 6 days at 12 degrees Celsius and then cold conditioned at 0 degrees Celsius for 7 days. It was filtered through cellulose sheets and then packaged in bottles. The clarity of the wort in the kettle was good, and the trube settling in the whirlpool was also good. In the wort receiver, we observed that 96.5 liters of the treated beer was collected at 11.1 degrees Plato. Just 93 liters of the control beer was collected at 10.9 degrees Plato. This test was our first indication that Polyclar Brewbrite stabilizer increased wort yield. The fermentation results show that the beer with Polyclar Brewbrite stabilizer and wort clarifier had a gravity drop of 9.7 degrees Plato and a peak yeast count of 65 million cells per milliliter. The control beer had a gravity drop of 9.5 degrees Plato and a peak yeast count of 47 million cells per milliliter. Polyclar Brewbrite stabilizer improved fermentation and had a positive effect on yeast vitality. This slide shows comparisons of tannoid levels at various points in the brewing process for the control beer and the test. In all cases, the treated wort gave better results for tannoid reduction than the control. Analysis of physical properties for the packaged beer revealed that most of the parameters were very similar for the test beer and the control. There was, however, a substantial reduction in haze for the treated beer. Polyclar Brewbrite stabilizer reduces haze but does not adversely affect physical properties. This trial showed that Polyclar Brewbrite stabilizer could increase wort yield, improve yeast vitality, lower tannoid levels, and improve clarity in the wort and the packaged beer. It also had no adverse effects on the physical properties of the packaged beer. Now we'll turn the page to some commercial trial results. This study took place at a U.S. brewery making a 100% malt lager at 13.5 Plato. The control beer used carrageenan alone at 3.9 grams per hectoliter, and the test beer used Polyclar Brewbrite stabilizer at 15 grams per hectoliter. The beers were fermented at 13 degrees Celsius for 6 days and then cold conditioned at 1 degree Celsius for 4 weeks. They were filtered through a horizontal leaf filter using diatomaceous earth and packaged in kegs and bottles. There was a marked increase in wort yield compared with untreated beer and beer treated with carrageenan alone. The increase in wort yield provides a substantial benefit to the brewery, making Polyclar Brewbrite self-paying. Beer treated with Polyclar Brewbrite stabilizer had undetectable tannoids and reduced total polyphenols. Protein content, as measured by PT standard and Saspol, was maintained. The addition of Polyclar Brewbrite stabilizer to the beer improved the predicted shelf life of the beer and reduced the amount of haze in the beer at each time point, compared with carrageenan alone, due to the decrease in tannoid levels. This trial was done in India with an adjunct lager at 15 degrees Plato. The control beer was stabilized with carrageenan alone at 2 grams per hectoliter, and the test beer received Polyclar Brewbrite stabilizer at 9 grams per hectoliter. Both beers were fermented at 10 degrees Celsius for 14 days and then cold conditioned at 0 degrees Celsius for 2 days. The beers were filtered through diatomaceous earth and then packaged in bottles. The clarity of the wort in the kettle was good, and the troop settling in the whirlpool was also good. The beer stabilized with Polyclar Brewbrite stabilizer had an increase in volume measured at the wort receiver compared with the beer stabilized with carrageenan alone. The beer stabilized with Polyclar Brewbrite stabilizer had a higher original gravity than the beer stabilized with carrageenan alone. The higher original gravity of the beer stabilized with Polyclar Brewbrite stabilizer also resulted in an increase in alcohol by volume. This case study took place at a brewery in Indonesia where an adjunct lager beer stabilized with 5 grams per hectoliter of carrageenan alone was compared to one stabilized with 5 grams per hectoliter of Polyclar Brewbrite stabilizer. Both beers were fermented at 10 degrees Celsius for 4 days, filtered through diatomaceous earth, and bottled. The beer stabilized with Polyclar Brewbrite stabilizer had a slightly higher original gravity than the beer treated with carrageenan alone. The use of Polyclar Brewbrite stabilizer had a noticeable impact on the amount of haze in the finished beer. At a brewery in Thailand, an adjunct lager beer with no stabilizer was compared with one treated with Polyclar Brewbrite stabilizer at 10 grams per hectoliter. The beers were fermented at 12 degrees Celsius for 7 days, cold conditioned at 0 degrees Celsius for 4 days, filtered through cellulose sheets, and bottled. The clarity of the wort in the kettle was good. The troop settling in the whirlpool was also good. The beer stabilized with Polyclar Brewbrite stabilizer had a slightly increased wort yield. Another benefit to the addition of Polyclar Brewbrite stabilizer is in the reduction of tannoids. The beer treated with 10 grams per hectoliter of Polyclar Brewbrite stabilizer showed a reduction in tannoids. The beer treated with Polyclar Brewbrite stabilizer also had reduced total polyphenols, further reducing the risk of haze development. A final trial took place at a brewery in Europe where an all-malt lager was treated with Polyclar Brewbrite stabilizer. Tannoids and polyphenols were measured both before and after addition of the stabilizer, and it could be seen from this slide that the use of Polyclar Brewbrite stabilizer led to a 49% reduction in tannoids and a 21% reduction in total polyphenols. In summary, the use of Polyclar Brewbrite stabilizers has a number of benefits for breweries. It enhances the clarity of wort in beer, increases wort production and ethanol yield, improves the total productivity of the plant, and extends the shelf life of packaged beer. If further stabilization is used downstream, even longer shelf life can be achieved. To summarize, beer must be protected from the haze instability caused by the reactions between haze-sensitive proteins and haze-sensitive tannoids. Haze-sensitive tannoid levels can be controlled by the use of Polyclar stabilizers. Polyclar Brewbrite stabilizer is proven to improve wort clarity and to reduce tannoid levels as well as increase wort yield and ethanol content. Polyclar Brewbrite stabilizer is completely removed from the beer, leaving no residue. Polyclar Brewbrite stabilizer can deliver substantial cost savings, and in many cases the product pays for itself. Thank you.